So we are about to continue our conference with the first speaker. It is Nikola Kamburov from the Facultad de Matemáticas Pontifica, Universidad Catolica de Chile, who is going to speak about one-phase free boundary subject to topological constraints. And I think we should abide by the program that we have roughly 1 hour, maybe 5 minutes for questions. We start late, but we have time afterwards.
Thank you, Professor Savo, for the invitation. Let me first start by thanking the International Center for Mathematical Sciences for organizing this fantastic event. Personally, I'd like to thank to academician Kamburov and to Antonio Rangace for the invitation. It's a great pleasure to be here. It's always nice to return to your mathematical roots. I'm excited to tell you about this long-term project that I've had with David Jerison from MIT, who was my PhD advisor, on the topological characterization of one-phase free boundary solutions. So this is a PD talk, and I realize that I'm facing a very diverse audience, so that's why I'm going to keep the technical level of the talk to a minimum. Okay, so let me first start by describing what the one-phase free boundary problem is. Okay, so it is one of the most basic free boundary problems, and because of that, it has been very well studied. In some sense, it's really one of the most fundamental ones. So in the one-phase free boundary problem, we are looking for a continuous function defined on a bounded domain in Euclidean space. In this talk, I'll be taking the domain to be usually the ball in Euclidean space. And we want this function to satisfy some certain fixed boundary conditions, directly, non type, non-mixed, etc. And in the interior of the domain, to satisfy the following conditions. So it has to be non-negative. In the set where it is strictly positive, which is called the positive phase, the function satisfies the Laplace equation. It is harmonic. Okay? And then on the boundary of the positive phase, which is interior to the domain, the so-called free boundary, the function needs to satisfy a constant gradient condition. So it is called, this set is called the free boundary because it has to be allowed to sit where it needs to be, so that on it both a Dirichlet condition, u is equal to 0 there, and a constant Neumann condition needs to be satisfied. If we just prescribe it a priori, then we would have an overdetermined condition for this function. So this problem models interfaces in fluid dynamics, interfaces between gas and liquid. It models jet flow. It's also used in optical insulation. But I'm interested in it for mathematical reasons, and the first major reason why this is an important problem is that it's a scale invariant problem. So if we take a solution u, boundary problem, then we can rescale as follows. And this rescale function will satisfy the one-phase free boundary problem in the rescale domain. The second reason why this is an interesting problem because it has a variational origin. So it is the Euler-Lagrange equation. These equations are the Euler-Lagrange equations associated with the following energy, the integral of the gradient squared, plus a potential term, which is the indicator function of the positive phase. It is precisely the discontinuity of this potential which produces this constant gradient condition there. The first object of study for this problem, of course, are the solutions that minimize this energy, the minimizers of the energy. This is the most natural first object to study. And those have been fairly well understood since the pioneering paper of Alvin Caffarelli from '81, in which they proved the following. So minimizers, energy minimizing solutions of the one-phase free boundary problem, satisfied in a certain weak sense. And of course it is the gradient condition which has to be, which one has to formulate in a certain weak sense. It needs to be satisfied. It is a so-called viscosity solution. I'll talk some more about it later. Inside the ball, the solution is Lipschitz continuous. And now, the really, really hard part of this study is understanding the regularity of the free boundary. Okay? Because if one has the regularity of the free boundary, then one will get the interior regularity of the solution as well. Okay? And what Alvin Caffarelli discovered is that modulo singular set of 0 and -1,000 door dimensions of measure, the free boundary is a smooth hypersurface. Okay? And therefore, on the complement of the singular set, the solution is smooth and the constant gradient condition is satisfied in the usual sense. Okay? So, yeah, this result on the singular set has been improved significantly since then through the works of Weiss, Catolica, Jerison, Mechanic, and Jerison and Sarin. And what one knows now is that the singular set has Hausdorff dimension, at most at -5. And it is conjectured that actually it is at -7. Right? And this is related to the existence of non-trivial, singular energy minimizing conic solutions. Okay, so this is very much in the spirit of what happens in minimal surfaces and the existence of the Simon's cone, which is a singular minimal surface, which minimizes area. And in fact, the paper by Alvin Caffarelli revealed a broad analogy between minimal surfaces and free boundary problems, which continues to drive progress in free boundary problems. And I'll try to convey some of that connection in the talk, which is in some senses way more than just spiritual connection. It's really in the flesh. So, okay, well, this is the story about minimizing, energy minimizing solutions. But what about higher critical points? So if one wants to then study solutions that are not necessarily minimizers, what is one to do? Well, now the space of solutions is very, very rich, and one needs to set criteria how to study it, how to organize the work. And one natural criterion is to impose a certain topological condition on the solution, and and study what happens to the free boundary. So the type of question that we'll be interested in is exactly the following one. So if we have a classical solution, and by that now I'm assuming that the free boundary is smooth, so that the gradient condition is satisfied in the usual sense. And if I don't assume that it is a minimizer, it solves the free boundary problem, that's it. And I impose a topological condition on the positive phase. Say it is a contractible set, or it has a bunch of holes in it. What can I say about the shape of the positive phase on an interior scale? How does the free boundary look like? So, this question is very much, again, inspired by what has been done in minimal surface theory. So now let me briefly talk about minimal surfaces. Introduce them. So minimal surfaces are submanifolds of Euclidean space in general, which only locally minimize area. Right? So they're not global minimizers of the area functional, they're again just critical points of the area. Yeah, physically they're realized by soap films. Soap films, the surface tension energy wants to minimize the area. And this condition of local minimization of area can be expressed with, I can't see it because of the zoom bar there, but it is expressed in the condition that the mean curvature of the submanifold is 0. The mean curvature is the trace of the second fundamental form, or more simply, it's the sum of the principal curvatures of the surface. So let me show you a few pictures of the classical minimal surfaces that we have all probably seen at some point. So this one is the catenoids. It really goes back to the dawn of the area, discovered by Euler and Lagrange in the late 18th century. Okay, so it is a complete embedded minimal surface in R3. It has two infinite ends, and it has non-trivial first homology group generated by the neck, the so-called neck of the catenoid, the shortest geodesic around. Then there is another classical fellow, the helicoid, which is an exquisitely shaped double spiral case surface, which is actually has the topology of a disk. It is homomorphic to the plane. And another one, and this is my personal favorite, is a complete embedded surface of infinite topology. Okay? So it is a it's a periodic surface in one direction. It's called the single periodic Scherk surface. And it has 4 ends at infinity, the so-called wings of the Scherk surface. And we have a whole family of these guys, which is parameterized by the asymptotic angle between the wings. And this is just a small, tiny sample of minimal surfaces in R3. If you want to have a look at how beautiful they are, there is a website maintained by Matthias Weber of Indiana University, which he aptly calls the virtual minimal surface museum. So really, really beautiful surfaces in there. So the question that minimal surface theorists are interested in, which we borrowed from them, is the following: how do you topologically classify all these surfaces? So you have the geometrical object, which again has a variational origin. If you impose on it on a certain topology, what geometric rigidity is forced by the topology? And some examples of classification results, of rigidity results. Shane in 1983 showed that if you have a complete embedded minimal surface in R3, which has 2 ends and finite topology, and finite topology here means finite dimensional homology groups, then there's only one possibility, it's the catenoid. Another result, more recent one, by Meeks and Rosenberg, says that, okay, if you are interested now in a complete embedded minimal surface, which has the topology of a disk, okay, then there are only 2 possibilities. it's either the plane, which is of course the simplest possible minimal surface, or the helicoid, this double spiral, spiral staircase. The proof of this second result is not easy, and it required the powerful tool of the Kolding-Minkowski theory. Okay, so let me roughly say what this is about. So Kolding and Minkowski were interested in understanding limits of sequences of embedded minimal surfaces in the unit ball of R3, okay, that have fixed genus. Okay. So you have the space of embedded minimal surfaces in the ball. Can you compactify this space? Can you prescribe it a certain topology so that each sequence has a subsequence with some kind of a limit? And in order to understand limits, of course, the key issue is to understand locally what the shape looks like. What is this local structure of a minimal surface of a given genus? Okay. The work is technical tour de force. It was published in 4 Annals papers in 2004, and it served as the basis for the classification result of Mix and Rosenberg. And in the case of where the genus is 0, so where we have complete embedded minimal surfaces in the ball of R3, which have the topology of a disk, the so-called minimal disk. What they discovered was a dichotomy. So either locally the minimal surface looks like a small graph of bounded curvature. So it is modeled locally after the plane. Or if the curvature starts blowing up, gets large, then a double spiral case, the helicoid structure starts appearing. Okay, so Kolding-Minkowski theory can be looked as the local variant of these global classification results, and in fact they are the necessary tool to prove the second one. So let's now go back to the world of free boundary problems. So we can ask the analogous question, and I'll ask it here David likes to remark is that this is very apt because the initials of the three geometers, a double HP, well, that's double canopy, so it's consistent. Well, we have this list of solutions now, and the question is it exhaustive? Are there more? More that have finite topology. Finitely many connected components, if you will, of the free knowledge. And a couple of years after the discovery, Jerison showed that indeed these are all the solutions that are entire and have finitely many boundary components. And he did it by discovering a link, a very deep link to minimal surfaces. Okay? So he discovered a correspondence. So if you have omega being the positive phase of one-phase solution, and u being the solution, then you can define the following map from the positive phase into the upper half space, where the third component is exactly the solution u. And the first two components are gotten by integrating the following complex differential, which is cooked up by the solution. And here it is. One really uses the harmonicity of u. Therefore, this is a holomorphic function. U doesn't. Yeah. This is known as the Weierstrass representation formula for minimal surfaces. Okay. So turns out that this map defines the minimal immersion of the positive phase into the upper half space. And even more interesting, so if one looks at where this minimal immersion, this minimal surface, which might have intersections, and where exactly it attaches on the plane x3 equals 0, and how? Well, how? It turns out that the free boundary condition, the constant gradient condition, translates to the surface attaching orthogonally to the plane. Therefore, one can reflect it and get a surface, which has a minimal surface, which has a symmetry, so-called minimal bigraph. Furthermore, turns out is that this map is an isometry acts as an isometry on the free boundary components. So the image of the free boundary is isometric to the free boundary. This works for bounded solutions in a bounded domain, but now if you go to solutions that are globally defined and satisfy the strict less than 1 gradient condition in the positive phase, then these are in direct correspondence with embedded minimal bigraphs. Okay. So you have embedded minimal bigraphs, a finite topology, and for reasons I'm not going to go into, they have to have two ends. So by Shane's classification result, this minimal bigraph can only be the cataloid. And now we can see where these solutions come from. So the exterior of a disk solution comes from the vertical cataloid. Okay, so where we consider cataloid with a plane of symmetry through its neck. And the horizontal cataloid comes again from the hairpin solution, double hairpin solution comes from the horizontal cataloid, meaning the cataloid but looks as a bigraph with a plane of symmetry orthogonal to the neck, okay, along a meridian. And interestingly enough, well, then what other minimal bigraphs are there? The short surface is a minimal bigraph. Okay, the infinite topology though. Okay, to it corresponds solution of the free boundary problem in 2 dimensions, which actually was, it was a rediscovered solution known in the fluid dynamics literature. So, it's like the zero phase is like a periodic train of bubbles. This is in the fluid dynamics literature, they're known as hollow vortices. And since you have a one-parameter family of these guys based on how the wings, or the asymptotic angle between the wings of the short surface are, there is a one-parameter family of these guys as well. And the angle between the wings gets translated to the slope at infinity of the solution. So you have for each s between 0 and 1 of these guys. And the bigger the s is, the bigger the bubble. So in this way, the global question was, global structure question was tackled. And we came in to deal with the local structure question. Okay, the analog of what Colin Euclidean concept. And so, again, specifically we had the following. We had the following problem. So, we are interested in a classical solution. Again, free boundary is smooth. It sits in the unit disk, and we're assuming that the positive phase is connected and has genus G, meaning there are G bubbles of zero phase inside. Okay, and then we look at the local structure at points of the free boundary which are sufficiently far away from the boundary of the disk. So we want to get interior rigidity estimates. So what we got was the following picture. So there is there are absolute constants, R0 which provides the scale, and K0 which provides a bound on the curvature. Such that if we look at this scale, free boundary, then we're either looking at one strand, one connected component of the free boundary which has curvature bounded by this constant, or we're looking at two strands nearby of bounded curvature, or if the curvature starts exploding, growing, it is due to a double hairpin solution. And on the next slide I have an illustration of these three cases. So case 1 is the one which is modeled after the one-phase solution. The second case 2, is modeled after the two-plane solution. And it's the case 3 where is modeled after the hairpin solution. And I say resemblance. Okay. So what do I mean by that? The resemblance is expressed in terms of a near isometry. So we have a map which maps the positive phase in each of the three cases to the positive phase of the model, and which preserves distance up to say 1%. To all scales up to this scale R0. Okay. And I forgot to say that this is our theorem in the first simply connected case where there are no holes. And then I'll tell you more about what happens when we turn on the holes. Okay, so most interesting, of course, is the third case. And in the third case, where we have the curvature blowing up, we also get curvature rigidity estimates. I'll describe now. So, in the third scenario, what we have the two two components of the free boundary are very, very close to one another. Separated by some epsilon distance. Then for some a on the order of epsilon, what we have, we can define a conformal map from the standard double hairpin domain at scale R0 to this approximate hairpin domain, okay? Which is a near isometry, so it preserves distances up to 1%, say. And we can get second derivative bounds on this conformal line, which then translate onto curvature estimates. So the psi allows us to relate the curvature of the approximate hairpin to the curvature of the standard hairpin in this fashion, which unfortunately cannot be seen because of it's a unit-sized quantity. It's a unit-sized quantity, and what this means is that since the curvature of the double hairpin scales like this, it's like A over Z squared, where Z is the distance from the origin. This means that the estimate here is a very good estimate. It gives us, the curvature of the approximate hairpin is essentially the same up to 1% the curvature of the standard hairpin at a scale Z about square root of A to that scale. Outside the scale, we no longer have the proximity of curvature, but we still have that the curvature of the hairpin is very close at unit size. It's unit size. So that's not too bad. It means that up to a whole unit scale, here, whole unit scale, the free boundary, except for this small region where it blows up, up to unit scale, it's pretty flat, the whole structure. Okay, so I'll now describe the connection with Kolding-Minkowski theory. Okay, so to some of these results that we got, they are analogous results in the minimal surface literature. So I'll start with the third case of the double hairpin structure. What Kolding-Minkowski showed was that if you have an embedded minimal annulus, so this is a minimal surface which has the topology of an annulus, has two loops, it's just spanning two loops. Okay? So if these two loops are simple loops on the boundary of the unit ball, and the surface has a small neck near the origin of length A. Small neck means shorter geodesic. There is of size A. Then they show that up to this scale, square root of A, the same as ours. Yeah, the manifold is diffeomorphic to the standard cataloid, with a diffeomorphism that preserves distance and curvature to within 1%. So, of course, as we know, the double hairpin is the analog of the cataloid. And using the Treize correspondence, we actually recover this result. Of course, not in the full generality, but in the case where the embedded minimal annulus is a bigraph. Of course, the Kolding-Minkowski result is much, much harder, because in 3 dimensions, more degrees of freedom. So, an analog now to what happens in our case 2 is the following result by Kolding-Minkowski. So, in our case 2, recall we have that the free boundary has these two strands, okay, and separated by 0 phase. In the minimal surface story, what we have are, say, we have a minimal surface which has 2 components. Each component is homomorphic to a disk. And the boundaries of these two surfaces are disjoint loops in the boundary of the unit hole. So, this is the precise analog, to the strands. Now we have just minimal disks. And so the result is that if the two if these two minimal surfaces intersect the small ball of radius c, where c is an absolute constant, then at this scale c, they're pretty flat. There are the graphs of a function gj, g1 and g2, such that the gradient is bounded by, say, 1%. So they're very, very flat. And this is the exact case of where, in this case, the minimal surfaces are pretty much parallel planes. So from just the topological condition that they are minimal, this comes the fact that they are very close to being parallel planes. There is no analog to our case 1, because in the so our case 1, where we just have one strand here, which would correspond to the minimal surface asking for a minimal surface which has the topology of a disk. The problem is that in minimal surfaces there is the helicoid structure, which has no analog in free boundaries. So there's no analog to our case 1, but there is an intermediate scenario which arises both in the Golding-Minicalzi papers as well as for us. It's what's called an effective removable singularity theorem. So a removable singularity theorem for, say, an elliptic equation says that if like the minimal surface equation, says that if your solution is defined on all but one point and satisfies the equation in all but one point, then it satisfies the ultimate point. And there is a more quantitative version of it, so-called effective, where you are assuming that the free boundary, or in this case the minimal surface, is undefined in a certain small ball and is defined outside of it. What they proved is that, if you have an embedded minimal annulus, so it has, its boundary has two loops. One loop sits on a very, very tiny ball of radius delta. The other loop sits in the unit sphere. Okay? So then there is a constant c, and of course a constant delta naught, measuring how small delta needs to be, such that if you look at scale c times delta up to unit scale 1 over c, the minimal surface looks like a minimal graph. So it's the graph of a Lipschitz function with a very small Lipschitz constant. So if we get like a result that says if the minimal surface is undefined on a small ball, and satisfies all these other conditions, that it's still very, very flat in scale c times the small scale up to unit scale. And this is a result, by the way, which is uniform in delta. This is important. Okay, the result in our world, the world of free boundary problems, is the following one. So we assume that we have a solution defined in an annulus in R2, and assume that the free boundary has consists of two strands. This is the annulus. Assume that the free boundary consists of two strands, disjoint ones, well, they could do wild stuff, I suppose. Well, at least a priori. So they connect, so this is the boundary. The boundary of the small ball to the boundary of the unit scale ball. And we show that, in fact, we have a similar estimate where from small, well, from a multiple of the delta up to some unit scale, the free boundary is actually a graph of a Lipschitz function with a very, very small Lipschitz constant. The main tool in our theorems is the following classification results of blow of solutions to the One-Phase free boundary problem. So we have a sequence which solves the equation in the unit disk. We're assuming that the positive phase is simply connected, and now we take a sequence of radii that go to infinity, and we rescale these solutions to the disk of radius RK, so a larger and larger disk. So we show that these guys converge, subconverge uniformly on compact sets to one of the candidates, either the one-plane solution, or the two-plane solution, or the double curving solution. So we use this tool to apply it to compactness arguments, which then tells us, tells us what local configuration of the free boundary is. That it is in one of these three cases, or after one of these three guys. And after we get, to a certain scale and a certain proximity to one of these guys, what we do is we apply conformal mapping techniques in order to get the distance and curvature rigidity estimates. So just very quickly, the ingredients for this global classification result. First one uses the fact that a solution of the one-phase free boundary problem is uniformly Lipschitz. The key basic lemma is the following one: that solutions grow linearly away from the free boundary, so-called non-degenerate estimate. If we're at a distance r away from a point on the free boundary, the solution grows c times r at least, and of course at most because of the Lipschitz boundary. And this is where topological assumption plays a key role. This is important because it says that in the limit, the positive phase is not going to collapse to the zero phase. And it also ensures that we have convergence of the free boundaries, Hausdorff distance. The other ingredient is the appropriate notion of a weak solution. And here we use a combination of two classical notions. One is so-called viscosity solution, which allows us to use the Alcafarelli theory, which once we get to a flat configuration, then the solution is actually smooth. And the other type is the variational solution, which allows us to use monotonicity formulas, which tell us what a solution looks like at small scales and at large scales. We start blowing up, when we do blow downs of a single solution. And okay, so these are the ingredients for the classification result. And as I mentioned, the curvature and distance rigidity estimates are achieved via conformal mapping techniques. Here, very briefly, to explain So what happens is that, well, we can have, so if U is the solution, we're on a simply connected domain, so we can define the complex conjugate, and this defines a holomorphic function. And the constant gradient condition implies that the norm of the first derivative is 1. And now, yeah, what one can do, if the function U is actually a conformal map, is to take the inverse, and then via the logarithm of the derivative of the inverse, one translates a problem obtaining nonlinear estimates for the free boundary problem to obtaining estimates for a linear boundary value problem. How much time do I have?
About
15?
10, 15 minutes.
Excellent. Okay. So what about the story? What is the story when we turn on the genus, when we allow bubbles of zero phase? Well, the problem is that they're related to non-degenerates. Sorry, to degenerates solution. So remember these guys. This is zero positive, which corresponds to the log z plus. These solutions do not grow linearly away from the free boundary, and they grow logarithmically. So when we look at blowdowns, then the positive phase of this collapses to 0. So yeah, we have to worry about this, but it is doable, discerning the region where these guys have an effect. And the classification result that we get is that in this case, yeah, blow-up limits subconverge to the usual suspects. And in this case, we also get this guy, the exterior of a disk solution. Or, of course, when the whole story is very degenerate, we just have bubbles, it's kind of at a large scale, you just have to go to 0. But yeah, this result then allows us to apply similar arguments and to get the local structure result, which in this case adds one more local picture, that of a single bubble. So in the remainder, I want to describe some directions from here on. Of course, yeah, these are all results in 2 dimensions. So let's go up a little bit to 3 dimensions. And of course, yeah, I have to say here that these topological characterization results can only be done in low dimensions, because just the higher dimension, there's a whole zoo of solutions that comes to life. So in 3 dimensions, we pose the following problem. If we have, it's the global characterization. If we have an entire solution, so defined everywhere, and we assume that both the positive phase and the 0 phase are contractible, can we deduce then that U, the solution, is up to rigid motion equal to the one-space, half-space solution x3 plus. To this problem, of course, now this global classification result would correspond a local structure result. So if one gets this rigidity result, then one expects the following local rigidity results. That if we have a solution in the unit ball and it's positive in 0 phase and contractible, then on an interior scale, one can get bounds on uniform bounds on the curvature of the solution. Okay. The curvature of the free boundary. So this is one direction. Another very, very interesting direction is, to me at least, is the following one. So remember, the one-phase free boundary problem comes from the following energy. The gradient u squared plus the characteristic function of the constant phase. Here we have this.
Да. Че не се вижда Никола.
Да. Лошото е, че всички те са...
Няма ли много?
Може би червена. Така по-добре ли?
Да.
So recall the one-phase free boundary energy is the gradient squared plus this discontinuous potential, the characteristic function of the constant phase, which looks like this. This profile. So what if we consider a modification of
this has been brand new, they say.
Well, we're not going to damage. The green works maybe a little bit better. So this discontinuous potential can be modified a little bit, and we can define a smooth transition between the zero phase and the one phase. Alright, so we have this modified version. Critical points of this new functional J satisfy a semilinear elliptic problem. And now look, if we have a global solution, globally defined critical point of this equation, of this functional, so globally defined solution of this equation, and we start taking blowdowns, well, the blowdowns are critical points of the functional J epsilon, where the f of epsilon converges as epsilon goes to 0 to the discontinuous potential. So we expect that at large scale, the solution of the semilinear equation, its level surfaces should behave like the level surfaces of one-phase free boundary problem. So then we make the following conjecture, very much in the spirit of the De Giorgi conjecture, relating the semilinear Alenkhan equation to the minimal surfaces. It's the same phenomenon, where, if you have a globally defined smooth solution to the semilinear problem, and here we assume that its level sets have the same topology as the level sets of a one-dimensional solution. Okay, so V, big V, is just a one-dimensional solution. This equation just satisfies an ODE. Then the topological assumption forces a rigidity on the solution. After rigid motion, this V should be the one-dimensional solution. Okay? And of course, we're assuming that this is happening only in low dimensions. We have made certain partial progress for the n equals 2 case because of the results that we have for the one-phase free boundary problem in 2 dimensions. But for n equals 3 is just very much an open problem. Okay, and the final direction, and final out of many because quite a few avenues, is the following connection between the topology of the positive phase, this criterion that we want to use to study higher critical points of the free boundary functional. But there's a natural way to study another natural way to study higher critical points. It's via the Morse index. Yeah. So what is the Morse index? Well, if we have a functional, we can look at its second variation at a critical point for the one-phase energy functional. It's given by this quantity here, the integral of the gradient of phi. Phi is the direction of the perturbation. From it, we subtract a surface integral over the free boundary over the mean curvature. And the Morse index of a critical point with respect to the functional is defined as the largest dimension for the directions of the perturbation, so that the second variation is strictly negative. So the question is there a relationship between, aspects of the topology, say the genus of the topology, etc., and the Morse index? And this is again very much inspired by results in the minimal surface literature, where there are beautiful bounds relating the Morse index to, say, the genus, the number of ends of a minimal surface, etc. So, what can we say in the context of a free boundary problem? Is there a connection between the topology and the Morse index? Another interesting direction to take. Well, I think I'm time, so I'll stop here, and I'll thank you very much for your attention.
Are there any questions?
Quite a few actually.
Oh, fantastic.
Maybe I won't be able to ask all of them, but I will ask this one.
Okay.
So, can you go to the slide which defines the problem in the beginning?
Sure. Okay.
Yeah, so if we look there, all the information about the problem is encoded in the shape of B and the conditions of B, right? The free boundaries.
Yeah.
The results is a result from what you have specified on B and the conditions on B. So,
Yeah.
let's say I have some problem. How do I know in which of those three cases we will have? Is there a
So you're asking if I know what happens on. So if I know my data on the boundary.
Yes.
Yeah. How do I figure out where do I land? It's a great question. Unfortunately, I don't have the answer to it. Yeah. What we get are a priori estimates. So if
the classification results are good. I don't think anybody can argue, but in order to apply that practically, you have a connection between what's happening to the fixed boundary.
So the point it's saying is the following: if the curvature, our work says if the curvature starts blowing up, it's gonna be coming from a hairpin. Yeah, that's what it says. Okay. So if somehow in our numerics we see that the curvature blows up, then necessarily it's coming from these lines. Yeah. So this is probably the best that I can say at this level. But it would be very, very hard to say, okay, say I have this very specific boundary condition. It'll tell me, I go along this direction, along this direction, along this direction, because actually all three cases could coexist, as in the picture. I have no way.
So can you get all three cases if you start?
Sure. Yeah. I think that's a good. It took me forever to draw it, so I'll put it on. Miniaturized feast on it.
So if you have, let's say, you're into dimensions, you have a circle, B is just a disk, everything is happening inside. Can you get all three cases from a disk? B in the disk? Doesn't topology of B play a critical role in what you get?
What plays a
topology of B? Okay, the boundary.
The boundary of B.
The
fixed boundary. I mean, of course, it's going to play. It's really going to determine which of these appear. Of course, absolutely.
No. My question is, in what part does it depend on the shape of B, and in what part on the functions, which the conditions?
So it doesn't really depend very much on B, on the shape of the boundary. No, because these are interior estimates. So these estimates hold in for general domains. I will be able to find. Again. I have this trichotomy. So at every point on the interior, it's going to look into one of these three possibilities.
Okay.
Yeah, and it doesn't matter the geometry of the ball in this case. Doesn't matter as long as I'm sufficiently far inside in the interior of the domain. this is the picture that I get.
Okay.
Yeah.
What about other hyperbolic and parabolic operators?
So we study. Yeah, I mean this is an elliptic problem. Yeah.
You can find free boundary. It's actually
for parabolic. Yeah. For parabolic problems. Yeah. It's.
Hyperbolic also correlate because a bubble in a tube, for example, will be a dynamical correlate. It will be parabolic.
Sure.
So
okay. It's certainly something worth exploring.
And obviously it will get a lot more complicated.
Yeah, no doubt about it. Yeah.
Okay.
Yeah.
I think that's not.
Yeah, thank you.
Are there any?
You mentioned in the beginning, the second slide actually, the singular set is conjectured to be
n-7.
n-7 couple of dimensions. Are there examples with n-8?
Yeah.
n-7?
Yeah, there are.
Examples are with n-8.
Yeah, so there is a singular cone in 7 dimensions that was discovered by number 7 by Jerison and Silva. And 7, there is global, degree 1 homogeneous solution of the free boundary problem. That is singular and locally minimizes the energy function.
The singularity is a point.
What?
The singularity of the solution.
It's just the vertex.
The cone.
Exactly. The vertex of the cone is where the singularity is. Out of it is outside of it is smooth. Yeah.
I have a second question.
Yeah. Okay.
Now, if you talk about relation with minimum surfaces, there is relatively new direction there developed by Andreno Hess and Fernando Marquez, which, for example, they proved the so-called Wilmot conjecture, which is minimal tori in S3, that they are already really rigid around the people tori. Is there any relation with that?
So,
this is something which Golden can also couldn't.
right.
That's why I'm asking.
Yeah. For this particular problem, no, I don't think so. But I wouldn't be surprised again if one can cook up some kind of free boundary problem where that mirrors those results. But and here maybe I'm overplaying the relation between minimal surface and free. Certainly in 2 dimensions it's very much there in the flesh. The rest of it is more the spirit, how the arguments are proved, how the regularity theory is established. Say it mirrors what has been done before for minimal surfaces. Right, and again, the blow up and the blow down analysis. That's why these cones are interesting. And the blow up, you get the blow, and you get one-dimensional homogeneous solution via the monotonicity formulas. So we have monotonicity formulas in the free boundary world. We have monotonicity formulas in the geometric world as well. So this is the level of the connection.
Can I ask? Thank you for your interesting talk, but what kinds of energy are you considering? And what is the connection between this energy and minimal surfaces?
what is the connection between? That is a good question. So what is the connection between this energy functional and say the area functional?
This is for any kind of energy.
Yeah. Pardon?
Is this equation for any kind of energy?
No. This equation is the Euler-Lagrange equation related to this particular functional. Okay.
And
so
can you indicate equation between energy, your energy, and minimal surface?
Yeah, no, not directly, no. No, so the connection in 2 dimensions at least is between the equations here, the Euler-Lagrange equations, and the minimal surface equations. Yeah, but not it doesn't extend to the level of energies. So
this is some kind of variations, yes.
Yeah, exactly. So just these are the critical point equations. Yeah.
Let's end the speaker again.